Hi, welcome back to Moose and Chemistry. This is Nuclear Chemistry Mass Defect and Binding Energy Lesson 3. Given the element thorium-228, what is the mass defect if thorium-228 is 228.0287911 AMU? How much binding energy is produced? Okay, and we know that one proton is 1.00728 AMU and one neutron is 1.00867 AMU. Alright, well let's go ahead and do this, okay? There's a couple things that we need to know. We need to know the actual mass of the nucleus. We need to know the number of protons and neutrons in the nucleus. And we need to know the mass of the protons and the neutrons. And that's what we need to know to find mass defect. And what is mass defect? Mass defect is defined as the difference between the mass of the nucleus and the total sum of the mass of the nucleons. And nucleons are defined as either protons or neutrons. And here's the equation that we're going to use. Delta M equals, in parentheses, ZMP plus NMN, close parentheses, minus M nucleus. It's actually a lot easier than it looks. Alright, so let's go ahead and do this. So let's go ahead and set the equation up. So we go right, delta M equals ZMP plus NMN minus M nucleus. Okay, so delta M then equals, of course, 90 protons for thorium-228. Okay, and we're going to go ahead and get the proton, so 00728 AMU, plus with our neutrons we have 138 of them. How do we figure that out? We just took the 90 subtracted from 228, we get 138, and we're going to multiply that by, of course, 1.00867 AMU, close that bracket, minus the mass that we were given to start with, which for thorium-228 was 228.0287911 AMU. Okay. So now here we go. So delta M equals 90.6552 AMU plus 139 this will be also an AMU minus 228.0287911 AMU. Okay. So now this is going to give us this. So delta M is equal to 229.85166 AMU minus 228.0287911 AMU. So the mass defect comes out to be 1.82228689 AMU. Alright, there's our mass defect. So we found our mass defect. Now we want to find the amount of energy, the binding energy. So the first thing we have to do is we have to convert the AMU into kilograms. And to do that, what we're going to need to do is the following. Okay, So let's get this started. So we go 1.8228689 AMU times 1.6606 times 10 to the negative 27 kilograms divided by 1 AMU. That cancels out, and that gives us 3.027056 times 10 to the negative 27 kilograms. Okay, so far, so good. All right, so now we're going to use this. We're going to use the equation E equals mc squared. So we're going to go ahead and we're going to try to fit this all in. So let's see here. So E equals 3.027056 times 10 to the negative 27 kilograms times let's see here, 3.0 times 10 to the 8 meters per second, which is the speed of light, squared. Okay, so when we do the math, E is going to equal 2.72435 times 10 to the negative 10 kilograms times meter square over second square. But there's an easy way to write this, and we have a space here. 2.72435 times 10 to the negative 10 joules per nucleus. And that's the binding energy. Well, guys, you be snarly, and we'll see you back here at Moosine Chemistry.